Alright, welcome back to our number theory and encryption slides. Let us keep on trucking and talk about the next thing. So, where do we stop? I proved to you that there are an infinite number of prime numbers, and that was one of the greatest proofs of all time. It's so beautiful. I hope that you understood it. Let's keep on trucking with some more number theory. So, here's a theorem called Fermat's little theorem. I guess it's really a French name, so it's Fermat. It's his little theorem, and it is going to tell us something about primes plus modular arithmetic together. So here's the theorem. I will not prove it to you. It's a little difficult to prove on a slide, but I'll give you a flavor for why it's true. So here's the theorem. If p is a prime number, and a is any integer that is not divisible by p, so a is not divisible by this prime number, then if you take a to the power of the prime minus 1, so minus 1 times, that will give you the number 1 if you're working mod p, which is weird to think about. You take any number that is not divisible by p, take it to the power of it of that prime minus 1, that gives you 1 mod p. So that's really odd. All right, that is Fermat's little theorem. So here is my hand-wavy proof of this. Essentially, every time you multiply a by itself, you take all the powers of it, they end up cycling through every non-zero element of ZP. And ZP is 0, 1, 2, all the way to p minus 1. Remember that? So that is the reason it works. Let me show this to you for p equals 5 and a equals 2. So you do 2 to the 0, for example, mod p, so mod 5, that's equal to 1. Okay, and then, 2 to the 1 mod 5. That is, of course, 2. That is equal to 1. That is equal to 2. If you do 2 to the 2 mod 5, that is congruent to 4, right? I'll just use the congruent sign now. 2 cubed mod 5 again. That's 8 mod 5. That's 3. Somehow I've gone to every non-zero number. I've gotten to 1, 2, 3, and 4 of mod 5 land, of Z5. And all that's left to do is have it wrap back around. So 2 to the 4, which is 2 to the p being 5 minus 1, 2 to the 4 is when it wraps right back around and becomes 1, because that's, what, 16? And yeah, you do mod 5 on 16, there's 1 left over. There it is. It shuffles right back. That's pretty cool. And yeah, that's what happens. And my little hand-wavy proof is that the only way for your cycle to restart, because it needs to keep cycling, the only way to restart your cycle is to get back to 1 so you can start all over again. Okay, eventually you need to get back to 1, and after you visited all the numbers, that is your last stop. Okay, that's my silly example. And remember that ZP is all the numbers that could have been gotten by doing a modulus operation by p. 0, 1, 2, all the way to p minus 1, and the ones that we're getting out of this are all the non-zero ones. All right, so that is Fermat's little theorem. I do not have the space to prove it to you here, but it is useful. All right, he had another theorem that was a bit more, a bit larger, I guess. That's why we call it the little theorem. Feel free to look him up on Wikipedia. He's a very interesting guy. Anything else do I want to say? So yeah, this is essentially, you can extrapolate from this that a to the p, if you do that mod p, that's equal to a. That's equivalent to congruent to a itself, mod p. Which makes sense. 2 to the 5, again, you're multiplying it by 2, and that's giving you the number 2. It's itself. So that's a corollary of this theorem. Let's keep on going. The next one may be our first proof of the correctness of a program in this class. And so let me teach you it. It's called the GCD theorem. It's going to lead to an algorithm that will give us a way to find the greatest common divisor of any two numbers very quickly. All right, so here's the theorem. Let x and y be two positive integers that you want to find the GCD of. Then, here's the theorem statement. Then, the greatest common divisor of those two numbers, your original x and y, happens to be the same as the greatest common divisor of y mod x and x. And those are two smaller numbers. X stays the same, but this number is going to end up being smaller than the original y. So that's useful. All right, and that's going to eventually lead to an algorithm that stops and gives us an answer. So this greatest common divisor of your original numbers is equal to this greatest common divisor of two other numbers. All right? So here is how we'll prove this, and this will lead to an algorithm. You can just replace this with this, right? That's the algorithm. We're going to prove that every factor of x and y, right, because that's what it means to be greatest common divisor, and it involves factors. So every factor, i.e. divisor, of x and y is also a factor of y mod x and x, because if they share the same factors, then they share the greatest factor, right? And the GCD is the greatest common divisor. So if they share every divisor, then of course they share the greatest one too, okay? And so this is going to lead to our actual real theorem. Here's what we need to show, and that will lead to this theorem being true, right? So here's what we really want to show. We want to show that if, for every f, x, and y, if I have these numbers that work like this, if f divides x and f divides y for a factor, right, f for factor, then this is true if and only if, biconditional, that f divides y mod x and it divides x. So saying this is equivalent to, that's what bidirectionality means, equivalence. Saying the left side is equivalent to saying the right side, all right? So remember what that is spelled out if you have this a side, if and only if this b side. The bidirectional, biconditional, is saying that a implies b is true and b implies a is true. You can go in either direction, okay? That's the idea. So I guess the arrow's flipped around, so it's kind of like this at first, right? It's the right arrow and the left arrow. You have A and B, and you have the left arrow over here. And of course, this is equivalent to B implies A. So that's what it means to be a biconditional. And this is going to lead to an algorithm because it's like recursive. It'll eventually stop because this is a smaller number. Something's getting smaller when we call the function. So that will give us our algorithm, and this is going to prove it. All right, so that is our theorem. And so we have to prove both ways. We have to prove A implies B, this side implies this side, and B implies A, this side implies this side. They are equivalent things. So we can split that up into two directions. We can go to the left to right direction and the right to left direction. And it's just going to be a direct proof either way, like assume this, prove this if we're going left to right, or assume this, prove that if we're going right to left, right? So that's our theorem. Let's prove it. All right, so if we're going left to right, we're assuming these two things are true, and we're trying to prove that these two things are true, okay? So that is helpfully written for us right here. And so let's see if we can use both of those to prove what we want to prove. So assume, right, assume, this is the part of the proof, assume these two things are true, assume this factor divides x, and it also divides y. Looks like I'm writing the word fly. Sorry, there we go. F divides y. By assumption, right, we have to show that both of these things are true, this and this. We can easily get that this is true, right, because we are assuming it. So by assumption, immediately, that one's easy. F divides x. No work there. This one's going to take a bit more work. So, okay, F divides y mod x. What does this all mean? All right, so y mod x, if you spell it out, right, what is y mod x? It is equal to, where's the theorem that we proved? I think it's this one. Anything mod anything else is equal to that thing plus a multiple of the modulus for some integer. Let's use that here. That's going to be helpful again. All right, so if I try to compute this, whatever y mod x is, and this will lead to the answer. Y mod x is equal to, we know that it's equal to y plus some multiple of x for some k, some integer k, some k. All right, now watch what happens. Y mod x, that's equal to this. We just figured that out. It's equal to y plus kx. Cool. Y plus kx, which is equal to 1 times y plus k times x. What is that, right? What is that? That's a linear combination of x and y. This is a linear combo of x and y. What theorem do we have about that now? they're all coming together. Dun dun dun. I think, is it this one? If I have this and this, then it divides any linear combination of those two variables. And what do I have? I can use this theorem right now, right? What is y plus kx but a linear combination of x and y, for which I know that this factor divides both of those. So I can apply my old theorem, therefore, oops, let me get rid of the circle. Therefore, I know that this divides, f divides this, and that is that. That is the same as y mod x. Therefore, f divides y mod x, which is a linear combination. All right. Therefore, f divides y mod x. So I had to use two of our previous things that we proved. The one to extract some information about taking the modulus, and the one to use some divides stuff, some divides information, plus a linear combination to get that this linear combination divides is divided by the original factor. Okay, so that is the left to right direction. So that's what I proved. The first one was easy. This one was a bit harder. We had to use our theorems. Let's do it the other way now. This is the left to right direction. So again, we are going to assume this and then prove that. And those two pieces together make the biconditional. Okay? So, all right, so assume these, prove this. All right, so assume those two things are true. Assume f divides y mod x and f divides x. Cool. Again, I'm assuming this. I can immediately show that f of x is true because I need to show both of those, f of x and f of y. So again, by assumption, f divides x. So all I need to work on is showing that f divides y is a true statement. So what is y mod x, again, but some y plus k of x for some k. And this is where it gets interesting. What is this but an equation, obviously? I can solve that equation for y. So here's my little equation. I'm going to solve it for y. And that will lead to another linear combination involving the things I know. Solve for y. And that gives me, so y is equal to y mod x. This is just beautiful. Y mod x minus kx. And what is this? There's a 1 out there, right? What is this but a linear combination of y mod x and x? What is a linear combo of y mod x and x? And so my theorem applies again. Probably forgot where it was. One of these. I'll scroll to it eventually. So if I know that x divides y and x divides z, then that x divides any linear combination of that y and z. All right? So just plug in things appropriately, and I know that this divides this, and this divides this, and y, I've discovered, is a linear combination of y mod x and x. So therefore, f divides y. We did ourselves a big favor proving that theorem at the beginning. Therefore, f divides y. QED. So those are the two pieces of our proof, the left to right direction, the right to left direction. Together, they form the biconditional, and so this theorem is true. And so the greatest common divisor of x and y is equal to the greatest common divisor of y mod x and x, because they share every divisor, the greatest one too. So that proves our original theorem, and now we have an algorithm that computes the greatest common divisor of two numbers. It's called the Euclidean algorithm. All right. So if you just do this kind of thing recursively, you keep replacing GCD of xy with GCD of y mod x and x, because we prove that those two things are equal, equality rainbow, then eventually you're going to get, like, this number keeps getting smaller and smaller on the left. Eventually this number will become 0. All right. And every number every number that is non-zero divides 0. 1 divides 0, right? Because it's equal to 0 times 1, right? 0 is equal to 0 times 1. 2 divides 0 because it's equal to 2 times 0, right? 0 is equal to 2 times 0. 3 divides 0. Every single number that is not 0 divides 0. And so the greatest common divisor of those two numbers, right? Because the greatest common divisor of 0 is infinity, could be anything. So the greatest common divisor of 0 and any number is that second number, right? Because that's the one bringing us down, okay? And so eventually this is going to stop. Eventually it'll become GCD 0 and some number, and 0 is divisible by everything, or it has every divisor. So then the greatest common divisor of 0 and that second number is that second number, because that's the one with that stops before infinity. All right? It only has a finite number of divisors. So that is that. That is our base case. Here is our base case. And that means, like, if we keep doing, like, playing this game, eventually we'll get down to ... GCD of 0z, and z is our answer for the greatest common divisor of our original two numbers. Okay, we just keep replacing with things that are equivalent. And so that is an algorithm, all right? So now we have an algorithm to find the greatest common divisor. It's called the Euclidean algorithm or Euclid's algorithm, okay? And so probably the very first algorithm ever created and written down, because Euclid lived back in like the 300-ish BC era. And yeah, this is like the first algorithm ever. We have just proven it to be correct. Cool, huh? So let's see here. Let us calculate now. Let's use this algorithm to calculate the greatest common divisor of 80 and 61. All right? So what does that mean? We're calling our GCD function on 80 and 61, and I don't know, 80 is x, 61 is y, that is a 6, sorry. And we just keep replacing, right? What is the GCD of 80 and 61 but the GCD of y mod x? So 61 mod 80 and the original x. So what is that GCD? So y mod x is going to end up what? It's going to be the GCD of 80. So y is 61, x is 80, y mod x is equal to 61 mod 80. It goes in 0 times with 61 left over. So all that really just happened was that they swapped 61 and then GCD of x second. So the numbers swap until you have the smaller one first, and then the algorithm really kicks in and takes over. All right, so, and then we're calculating the GCD of 61 and 80. Now, for those ones, what is the result? GCD y mod x, so 80 mod 61. 80 mod 61 ends up being, I think it's 19? Yeah. So that's 19 on this side, and then the original x goes over here to the right. All right, so now it's 19 and 61, and now I'll do it a bit faster. So now this is the GCD of, let's see here, 61 mod 19. I guess I programmed it, but let's check our answer first. Python 3, 61 mod 18, that is the number, or sorry, it's 19, isn't it? 61 mod 19, that's the number 4. So this gives me 4. And then x goes over here. And again, GCD of x and y is equal to the GCD of y mod x. So 19 mod 4, 3, and the original x, so 3 and 4. And then we have GCD, we'll get there eventually, the GCD of y mod x, so 4 mod 3, that is 1, and then x, so that's 3. That's equal to the GCD of y mod x again, 3 mod 1. It goes in 3 times with 0 left over, right? So 0, finally, and then 1. Ooh. So GCD of 0 and 1, GCD of 0 and anything is that anything, that second thing. So the GCD of those two numbers is 1, and so they are relatively prime. Isn't that fun? So that's how you do it. And here's me programming it in Racket. You just saw it, but let me go back to it now. So, and then I'll run it right here. Whee! Off it goes. So let's see if I can get them both in frame. It looks like I can. So here's the GCD function. It takes two numbers, and it is recursive, but I'm just going to print before I do anything, just what I'm being called on, so you can watch the stack unwind. And then we have an if statement, a Racket kind of if statement. If x is 0, that means we have the GCD of 0 and something. The answer is finally that something. Otherwise, we use recursion. Otherwise, return the GCD of y mod x and x. And so eventually it'll work out. And so here is me calling GCD of 80 and 61. And you can watch it like work and call smaller things that it needs to call. 80 and 61, 61 and 80, 19, 61, 4 and 19, 3 and 4, 1 and 3, 0 and 1, and the answer is 1. All right? And then here's another one, 12 and 18. The GCD of those two numbers is just 6 because it calls 12 and 18, 18 mod 12, that's 6 and 12, and then 12 mod 6 is 0, and so the answer is 6. That's the biggest thing that goes into both of them. Okay, so that is that's GCD in a nutshell. That's how you can program it in Racket, and yeah, that's the algorithm. So with this in mind, just burn this into your mind. I have a question for you. So maybe pause it, write down this equation. Now you try. Find the GCD of 42 and 30. Okay? And this is like 42 is your x, 30 is your y. And my hint to you is you don't have to like write it out like this. You can do it a bit faster. Just keep on writing like y then x and then taking the modulus of the two things right next to your pencil. That will make sense if you try it, but I'll show you at the end. Okay? So give that a try. And let's write down what happens. So here's the trick. You write y, so 30, and then x, 42, because you're eventually going to have to do y mod x, and then x again. And then x is right here anyway. So here we go. 30 mod 42. What is that answer? Well, it goes in 0 times with 30 left over. So now it's 42 and 30. Now we're calling GCD on 42 and 30. All right? Where this is the new x, this is the new y. That's the idea. We're writing it backwards like that, and that's going to allow us to just keep on doing like mod in between here. Okay, so now it's 42 mod 30. What is that answer? It is 12. And again, this is the new x, this is the new y. Went for the other call of the function. I'm writing it backwards because I can just now easily do a mod here. You see how pretty that is? 30 mod 12, 12, 24, I think it's 6. Yeah, there's 6 left over, so the answer there is 6. And now this is the new x, this is the new y. What's 6 mod 12? That is 0, and that's my stopping condition. That's not the answer, that's just the old y when I did that. Now, the GCD of 0 and 6 is just 6. And so that's how you solve it, by just writing a line of numbers. Okay? If the first, if x is bigger than y, they're going to swap. That's the very first thing they're going to do is swap. And then it starts working its way down. Okay? It's a very fast algorithm, and that is a good example. All right? Here is a funny intermission, and with that, I would like to teach you a fancier thing that you can do with Euclid's algorithm, with the Euclidean algorithm. So, not just can you quickly find the GCD of two numbers. No, Euclid is going to do even better than that for you. It turns out that you can express the GCD of x and y always as a linear combination of those original numbers of x and y. So here is that in a real mathy kind of statement. If x and y are two numbers, then there are two integers such that, s and t, such that the greatest common divisor of x and y is a linear combination. It's s times x plus t times y. It's a linear combination of those original two numbers. All right? And this is useful to us eventually. It's going to eventually make a whole lot of sense why we're learning this, but we have to wait. Encryption is the real reason. All right? So the Euclidean algorithm can be extended to make this happen. We just need to save some extra information. What you do is you take this scratch work that you did while you were finding the GCD, and then you kind of work backwards from your 0 and 6 to your 12 and your 30 and all that kind of stuff. It'll make sense with an example. But you're going to work backwards from your scratch work, and remember that you can do stuff with your division algorithm, right? If you're dividing things, and we were doing the modulus, right? We got an r. We can relate the two numbers that we were taking the modulus of. Like, this was our original number, this was the thing, this was our modulus. It's equal to q plus r, q times our divisor plus r. We can solve for r. All right, that's going to be helpful. And yeah, for us, n is our y in the algorithm. D is our x, because we're doing y mod x, so we're dividing by x, getting the remainder. So r is equal to y mod x, and q is equal to y div x. So let's write that all out. So this equation, that's the division equation, with these variables in mind, the things that we were actually trying to do with our GCD, x and y. So I'm trying to take y mod x, right? And so what happens in the division algorithm? Well, it's y is equal to, once I do that mod, it's equal to the q times the divisor, which was the modulus. So y div x, that's the quotient, times the modulus, which was x, so I'm doing y mod x, plus whatever the remainder was, and the remainder is y mod x. That's how we write it, right? So that's the equation that you have when you use the division algorithm. You always know that this is true. We can solve this for r, which is y mod x. So y mod x is always equal to your original y minus y div x times your x. And what is this but a linear combination? You can keep on like plugging in older and older values, and this is going to give us our answer. So I'm going to highlight it in rainbow because it's so important. So just keep using that, and eventually it all works out. So let me show that to you. Let's see, as an example, let's do 675 and 210. Let's do the GCD of those two numbers. Let's express the GCD, which I don't know what it is yet. I think if I look at my notes, the answer is 15. The GCD of these two numbers is 15. We're going to be able to express that 15 in terms of a linear combination of the two original numbers. All right? So here's how you do it. So 675 and 210, you write it backwards, 210, 675, and then you just start taking moduluses of the last two things you wrote. So 210 mod 675, they just swap each other. That's 675, 210, what's that modulus? 675 mod 210 is 45. 210 mod 45 is 30. 45 mod 30 is 15. And 30 mod 15, it goes in cleanly, so it's 0, so the GCD is 15, okay? And now, here's what you can do. To get that 15, what did we do, right? We used the division algorithm. We did 45 mod 30. This was our x, this was our y, right? We did y mod x to get the 15, and we can express 15 in terms of 45 and 30. How? Like this, our division algorithm, right? Let me use this equation first. So we did 45 mod 30. Using this, y is the 45. 45 is equal to, by the division algorithm, something involving, some quotient involving 30. So it was just 1, right? It was equal to 1 times 30 plus the remainder, which was 15. And you can always check yourself, like, of course that works. 45 is equal to 1 times the 30, the thing that I was taking the modulus by, dividing by, plus the remainder, 15. All right? And so we can transform that, of course, into this form. So let's do that now, and I'll go back to blue. So that means we can solve for the 15. 15 is equal to 45, right, minus 1 times 30. And that's a linear combination of 45 and 30. So I've just expressed 15 as a linear combination of 45 and 30, and now watch what I can do. I can keep on plugging things back in, all right? Because I'm going to just keep on working from right to left. I have, what is 30, right? I have a value for 30, too. 30, I guess I can use a different color. 30, I also know how to get 30, because it was 210 mod 45. I can get 30 as a linear combination of 210 and 45. Can't I? Using that equation again. So let's do that. 30... I'm just going to have a bunch of equations involving like these three things, then I shift over, these three things, then I shift over, then it's these three things. It'll all keep working. All right, so 30 is equal to, well, it's 210, just following this idea, 210, that was the thing I was dividing, by 45. So it's 210 times something, or it's just 1, minus some multiple of 45, right? So what is the answer? 30 is equal to 210 minus something times 45, and the answer is 4. 4 times 45. That gives me 30 if you solve for that number. And so that's just integer dividing 210 and 45. So that's the 4. So it's equal to 4 times 45 subtracted from 210. So that's how I get 30. Now let's do the same for 45 involving 675 and 210. 45, because then I can plug that in right here. See how that keeps working? What is 45? Well, it's a linear combination of 675 and 210 because I had to modulus those two to get the answer. So 45 is equal to, following this idea, it's equal to 675 minus that quotient, y div x, so 675 div 210. It's 2 slashes in Python, so it's 3 times 210. That gives me 45, my remainder. So you can always solve for these equations like this, and what do you know? This, 45, is equal to a linear combination of my two original numbers, and then what's 45 but stuff involving the next numbers, and stuff involving 30, and then what's 30? That's stuff involving, I can solve for it in terms of the other things, and eventually end up at 15, all right? Because that's the answer. I'll eventually end up with some multiple of 675 and 210, give me 15, and let me walk you through it, all right? Once you do this process, solve for 15 in terms of 45 and 30, solve for 30 in terms of 45 and 210, solve for 45 in terms of 210 and 675, you can bring all these three equations together and get a linear combination of your original two numbers, giving you the GCD. All right, so let me walk you through that. Let me take these, let me copy them. There's a lot going on here, but I'm going to try and highlight it for you as best as I can, and then I'll have you try it. So plenty of examples. So those are the equations we found are true, and we want to involve 675 and 210 and have that give us 15. All right, so that's where we're going with this. So 15, we can start with that one. 15 is what we really want. It's equal to 45 minus 1 times 30. All right, and eventually we need to get this in terms of 675 and 210. We can do that by noticing that I know what 30 is. It's equal to this, and that gives me numbers closer to what I want. So let's replace this 30 with what it's equal to. What's 30 but, well, keep the 45 minus 1 times. What's 30 but 210 minus 4 times 45? 210 minus 4 times 45. And now we have to do some factorization and things. 4 times 45. It's just equalities. And that's equal to 45 minus 210. And that's plus, right? Because it's a minus and a minus. Plus 4 times 45. Get all the 45s together. So that's equal to how many 45s? 1 and 4, so 5 total, 5 45s, minus a single 210. And now I can play this game again. So 210 is one of the numbers I need. Let's replace now the one I didn't want, 45. I have something for 45. I can replace it with this. 45 is equal to 675 minus 3 times 210. So this is equal to 5 times, and I'll replace the 45 with what I know it's equal to. Getting closer to my answer, 675 minus 3 times 210, and then minus that original 210. And this is like the last step. I have 5 675s, and then minus 15 times 210, and then minus another 210, which is equal to 5 times 675 minus 16, right? Minus 1, minus 15 and minus 1, so minus 16, 210s. And that, my friends, is the answer. So 15, this thing that I was getting at, this thing that I needed, 15, is equal to 5 times 675, my original number, minus 16 times 210. This was my linear combination. This is my S, this is my T here. S, T, I guess T is technically negative 16, but you get the idea. I've made two I found those two numbers such that when I multiply and take a linear combination by those original numbers that I asked for the GCD of, the 675 and 210, that was my original question, right? I have now expressed the GCD of 15 in terms of those. That is the extended Euclidean algorithm. It's very extended, right? Let's confirm that it worked. I have 5 times 675 minus 16 times 210. And what do you know, that is 15. So that is how you can express the GCD in terms of your original two numbers as a linear combination, which is probably as good as it gets. All right? So here's a slide you might want to stare at for a while, and then definitely go to this example and stare at it too, because I want you to try it now. All right? So here is a question for you. Take a little while. Try it. Represent the GCD of 42 and 30. So do the GCD first, and represent it as a linear combination of those two numbers. So you use the extended algorithm. All right, so give that a try, and then I'll show you how I do it. All right, did you get it? So as usual, you start by taking the GCD as normal as we know how, as we did up here. So I just copy and paste that, but do it all over again. 30 and 42, it's y then x. So 30 mod 42, they flip, comes 30. 42 mod 30, that was 12. 30 mod 12, that was 6. And then 12 mod 6 was 0, and that is the final answer. And now we go from here, from these things, to equations involving the last three numbers. So equation involving those, and equation involving those, and that will give us all we need. So let's represent 6 in terms of the things that we took mods from, right? Because that's how we got it. So let's represent 6 in terms of 30 and 12, because this was what? This was y, this was x, and this was y mod x. And that was our linear, or not our linear combination yet, that was our GCD. Okay, so let's go from here to our equations now. Let's represent 6 in terms of 30 and 12. 6 is equal to, by what we saw, let me write that bigger, 6 is equal to, well, it's 30 minus some multiple of 12. It's 2 times 12, right, to get 24? 2 times 12. And that's how you get 30 in terms of, that's how you get 6 in terms of 30 and 12. It's a linear combination of those. And then we can just like shift over and get 12 in terms of 42 and 30, because that was another modulus relationship. So what is 12 but 42 minus, well, it's just 1 times 30 actually. 1 times 30. That one's easy to do in your head. Sometimes you have to break out a calculator and do integer division though. And now you bring those two equations together. So you start with this one. You start with the one that has your GCD, 6 equals 30 minus 2 times 12. And then you plug in this one in that. So now I can replace that 12 with things. So 6 is equal to 30 minus 2 times, what was 12 but this? 42 minus 30. 42 minus 1 times 30, which is just minus 30. And so let's get these all together. That's 30 minus 2 times 42 plus 2 times 30. Right? Remember that the minuses cancel each other out there. And so how many 30s do I have? I have 1, 2, 3 of them. So it's 3 times 30 plus, minus 2 times 42. And that is my linear combination, 2 times 42. So here is my original two numbers, 30 and 42, that I took the GCD of. The GCD is 6. That is equal to 3 times 30 minus 2 times 42, a linear combination of those two numbers. Okay, so that's the extended Euclidean algorithm all over again. I hope it's still making a bit of sense. All right, so let's see here. The next and final topic of the day are about multiplicative inverses. So I would like to teach you a little bit about those guys, multiplicative inverses. So a multiplicative inverse, it's a very long word, mod n, that's important, a multiplicative inverse mod n of some number is a number, right? It's in mod n land, so it can only be between 0 and n minus 1, but it turns out that it's never 0. It's a number between 1 and n minus 1, such that when you multiply your number x by this inverse thing, you end up getting 1 in mod n land. So it's essentially, that's what it means to be an inverse, right? The inverse of the number 4 in normal number land is 1/4, because, right? Because when you multiply them together, you get 1. because 4 times 1/4 is equal to 1. They cancel each other out. That's what it means to be an inverse. And so this is what it means to be an inverse mod n land. If you multiply those two numbers together, you get 1 after doing mod n. Okay? You're working in Zn, essentially. You can actually, another reason that we used extended Euclidean algorithm, the reason we learned that, is you can use it to calculate the multiplicative inverse mod n of some number, which is going to be great. All right? So that will be very helpful for us. And so let me show you, let me walk you through it. You are going to take the GCD. You're going to take the GCD of the number that you want to find the multiplicative inverse mod n, and you're going to take it with the number that you're doing the mod from. All right? You're going to find the GCD of the number and the modulus, so x and n. All right? So you're trying to find the multiplicative inverse of x mod n. You give them both the GCD. And you have to confirm that they're both 1, all right? Because otherwise the inverse doesn't exist, all right? So if this is ever true, right, if you can find 1, if the answer is 1, if they're relatively prime to each other, then you can find two numbers, right, using extended Euclidean algorithm, s and t, such that x times s plus n times t, linear combination of those two things, equals 1, which was the GCD, okay? And so this will find us our inverse, right? If you take mod n of everything here, right, this all goes away. This n part, this goes to 0, right? Because if you're taking mod n, any multiple of n does nothing. It just causes it to wrap around the clock again. So this equation, once you do mod n, it turns into s times x equals 1 mod n, and that's exactly the inverse that we wanted to find, okay? So yeah, the answer, the final answer, once you use this algorithm, is whatever s is, but make sure it's mod n, right? It's got to be one of those numbers. It might be negative. You got to fix that. So s mod n, whatever that is the multiplicative inverse of x. Isn't that cool? Mod n, of course. All right, so with that in mind, let me show you how to find the multiplicative inverse of 7 mod 10. All right, let's do our algorithm and figure that out. So you have to take the GCD of 7 and 10. And so if you write it backwards, 10, 7, what's 10 mod 7? That is apparently 3. 7 mod 3 goes in twice with 1 left over. What's 3 mod 1? That's 0. And so you stop, and the GCD of the thing right before it is your real GCD. So it really is 1. The answer is 1 here. Cool. And now let's use our extended Euclidean algorithm to relate 7 and 10 and create 1 out of it. Find those s's and t's that give us 1. All right, and then we can cancel things out. So what is 1 involving 7 and 3? 1 is equal to 7 minus 2 times 3. That's the 6. And then what is 3 involving 10 and 7? Well, again, that's an easy one. So 3 is equal to 10 minus 1 times 7. So just 10 times 7. Or 10 minus 7, excuse me. Lots of numbers. Got to keep straight in your mind. So with that, we can start plugging things in. So 1 is equal to 7 minus 2 times 3, but 3 is equal to 10 minus 7, so let's replace that. 7 minus 2 times what's 3? 10 minus 7. Let's get these all by themselves, and that is equal to how many 7s? It's 1 and then a plus 2, so 3 7s total, minus 2 times 10. And so that is my linear combination of 7 and 10 that gives me 1. And now I'm trying to find the multiplicative inverse. Remember our original job. I'm trying to find the multiplicative inverse of 7 mod 10. So I'm going to take mod 10 in this equation on both sides. Because here's my final equation, right? It was 1 is equal to 3 times 7 minus 2 times 10. I'm taking that whole thing mod n, which was what? That was mod 10, mod n, which was 10. If I take mod 10 on both sides, then the 1 stays the same. This is all the same. And then the 2 minus 2 times 10, that all goes away to 0. All right? That whole part goes away to 0. So the answer is 1 is equal to 3 times 7. And the multiplicative inverse then of 7 mod 10 is the number 3. It was the thing that I multiplied it by to give me 1 mod n. That's what it means, again, to be an inverse, right? You multiply it by its inverse and it gives you 1. This is the multiplicative inverse of 7 mod 10. And this makes sense, because what is 7 times 3? It's 21. Mod 10 that is 1, right? There's 1 left over. And that is your unique inverse mod n, multiplicative inverse mod n of a number. Okay, this will prove to be very, very important. We need this for encryption, and so we have to learn it now. So let's just get some practice with it. Let's see, is there anything else that I would like to mention here? No, I think that makes enough sense to me. So yeah, just remember that everything goes to 0 when you take the modulus of things. Okay? So here is a job for you. I have 2 different numbers this time. Find the multiplicative inverse of 35 mod 48. So some number such that when you multiply it by 35, it gives you 1 when you do mod 48 at the end of all that. Okay? Multiplicative inverse of 35 mod 48. The order of those numbers are very important, because the 48 is the thing you're taking the mod by. All right, so here's that informational slide, and here is your job. Okay? So give that a try, and then I'll give you some hints, and do it in full. So that is, let me just write this out. That is, I need to find something that when I multiply 35 by it, that is find, we were calling it S, find S such that, I will abbreviate such that as ST, find S such that 35 times S is equal to 1 after I do mod 48. And this is an S. Sorry, it looks like a 5 times S mod 48 is equal to the number 1. Okay? So that's what you're trying to find. All right, so let's do 35 mod 48. We're going to find the GCD of those 2 numbers first, 35 and 48. So 48, 35, 48 mod 35 is apparently 13. 35 mod 13 goes in twice to make 26, and then there's 9 left to make 35. 13 mod 9, 10, 11, 12, 13, 4 is left. 9 mod 4, that is 1 left over. And 4 mod 1 is 0. So the answer is 1. The GCD is 1. That's great. That's what we needed. And let's keep on going. Let's represent 1 in terms of 4 and 9. So 1 is equal to 9 minus 2 times 4. Let's represent 4 in terms of 13 and 9 using our extended Euclidean algorithm. 4 is equal to 13 just minus 9. That works. And then let's represent 9 involving 35 and 13. 9 is equal to 35 minus 2 times 13. And then finally, let's represent 13 involving 48 and 35. So 13 is equal to 48 minus, it's just 1 times 35. All right? With that, now we start solving for some linear combination of our original numbers that give us 1. So it's a lot of plug and chug, but I think you get the idea. I'll use a different color. So 1 is equal to 9 minus 2 times 4. I'll go a bit faster. 4, though, what is 4 but this? So this is equal to 9 minus 2 times 13 minus 9, which is great. So that's equal to how many 9s? It's there's 1 plus 2 more, so 3 9s minus 2 13s. And what is 9 now? I can plug in this for 9. So that's equal to 3 times, what was 9? 35 minus 2 times 13 minus another 2 times 13. Cool. All right, how many 35s? 3 times 35. And how many 13s? It's going to be, let's see, we have minus 6 and then minus another 2, so I think that's minus 8. Minus 8 13s, giving us 1 again. But what is 13 but all this? So let's, one last time. 3 times 35 minus 8 times 13 was 48 minus 35. And this finally is equal to how many 35s? I have 3 and then plus another 8, so positive 11 times 35 minus 8 48s. All right, and so now I have these 2 numbers equal 1 when I found the constants out in front of them. And so what happens? I'm trying to find the multiplicative inverse of 35 mod 48. So I'm going to take mod 48 of both sides. So this side still stays 1, and then any multiple of 48 over here goes away to 0. All right, And what I'm left with is some number times my 35 that gives me 1 when I do mod 48. All right? So here's the answer. It is 11. And if this happened to be a negative number, you want to make it a number that mod 48 could give back between 0 and 47, right? So you'd have to add 48 to it or something if it was negative to get it to be the right range. And so 11 is the multiplicative inverse. And you can confirm that by doing 11 times 35 and then doing mod 48, because that was always the thing we cared about. We're working in Z48. That's equal to 11 times 35. What is that? 385. 385 mod 48. And then, obviously, the answer to that should be 1. We can confirm that, though. Oops, not 47. 48. Yay. It is 1. That is its inverse. 11 is 35's inverse in mod 48 land, I would say. All right? That's how I think about it in my brain. So that is the extended Euclidean algorithm used to find this thing called a multiplicative inverse, which maybe looks weird and not useful, but I promise you this is going to come in so much handy when we study our RSA encryption algorithm. So we'll get there in just a second. You'll just have to wait till next week. All right, so I think the final thing that I want to talk about is your next lab, and so I will see you in the lab introduction video.